For this video, I'm going to show you how matrix multiplication works in Numpy in 1 and 2 dimensions. Now, I will make a video on 3 dimensions, but I find that gets a little more complicated then, and it takes a little more explanation, so I'd rather make a separate video for that. Alright, we'll start with the rule for matrix multiplication, which is if you have a matrix of n rows and k columns, and then you matrix multiply it with a matrix of k rows and m columns, that will work. And the reason for that is because k is equal to k. So these two shapes of the matrices, k has to be equal to k over there. And then the resultant matrix is going to be an n by m matrix. So this is just the same rule from maths, essentially. Now let's look at this example. Alright, so we have two arrays here, and they are matrices, and the reason for that is because they have 2 dimensions. They do look like vectors because they only have values in 1 dimension, but they are matrices. And what we'll do with these is let's take we need to define Numpy. Let's take a look at the shapes. So if we look at array 1 shape and then array 2 shapes, we get a 1 by 3 matrix and a 3 by 1 matrix. Will this work? Yes, because k is equal to k over here. So it will work, and it's going to produce a 1 by 1 matrix. So let's take a look at this. And it prints out 32, which is equal to the dot product, essentially. So when you have 2 vectors, the matrix multiplication is essentially a dot product. So you have 4 times 1 plus 5 times 2 plus 6 times 3, and you get 32. Alright, let's take a look at the second example down here. So this one is 2 matrices again. I'm just going to comment this out here. And I'll show you the shapes. So array 1 dot shape and array 2 dot shape. We have a matrix that's 1 by 3 and then a matrix that's 2 by 1. Will this work? No, because these two elements are not the same. 3 is not equal to 2, so it won't work. If these two elements were the same, it would produce a 1 by 1 result, but it doesn't work. And I'll show you. If we print it out, we get an error. And basically it says that, so it shows this rule here where nk and km, k has to be equal to k essentially. And these two values are not the same. So that's what it's saying here. And that's why this one doesn't work. And if you think about it, how would you matrix multiply anyways? 4 times 1 plus 5 times 2 plus 6 times what? It doesn't really make sense. Alright, let's take a look at... these are a few examples actually, because I want to go over a way that Numpy does this. A rule that Numpy has for these. Alright, so this second... Actually, I should move this up here. This one here, this is exactly the same as the first example that we gave. So this is the same as this one here. I've just reprinted it. If we run it, we get 32. And now this one is almost the same as the first example, except array 1 is now a 1-dimensional array. See, so this one has 2 brackets, this one only has 1. If we print this, we also get 32, but it's slightly different. It only has 1 bracket compared to 2. Now this one, it has the same values, but now these are vectors. Now these are both 1-dimensional. So we have 4, 5, 6, and 1, 2, 3. And it's 32. Now you might wonder why this works, because if you look at the shapes here, let's take a look at the shapes for these ones. So I've run this cell here, the one in the middle, and I'm just going to take a look at the shapes. Or actually, I'll print it in the same cell so you know what's happening. Print array 1 dot shape and then array 2 dot shape. So if we take a look at these, we have 3 comma nothing because this one is only 1-dimensional, and then we have 3 comma 1 because this one is 2-dimensional now. So 3, that's the columns. Oh no, that's the rows. 3 is the elements through the column, or 3 is also equivalently the number of rows. Does this make sense? I'll write it up here. We have 3 comma and then 3 comma 1. is this value here, which is non-existent, equal to this value? It's not, because it's non-existent, so it doesn't really make sense. But Numpy has a rule for this. If we take a look at the documentation, this is just the numpy.matmul documentation. They have some notes here. And the notes I'm interested in is these two over there. If the first argument is one-dimensional, it is promoted to a matrix, so it's promoted to two-dimensional, by prepending a 1 to its dimensions. So by adding another dimension before all the other dimensions, so on the most outer dimension, that's the prepending. And then after matrix multiplication, the prepended 1 is removed. And this second one here is if the second argument in the matrix multiplication is one dimension, it is promoted to a matrix to two dimensions by appending a 1. So a 1 is added to the very right of the shape, to the most inner dimension. And then after matrix multiplication, the appended 1 is removed. So it looks like that's what's happening here. This first array is one-dimensional, so it's not a matrix, so the rule applies. So if we take a look at the rule again, if the first argument, that's the case that we're in, is one-dimensional, it is promoted to a matrix by prepending a 1. So instead of 3, nothing, the shape is now going to be 1, 3, because we're prepending a 1 in the dimension. And then once we've done that, 3 is equal to 3 here. So the resultant matrix, the resultant array, is going to be 1 by 1. And that's why if we run this, it works and we get 32. I'll explain why it's slightly different in a second, but let's just take a look at this other example here. So this one works as well. And you might be wondering why, because again, if we take a look at the shapes, we get 3, and 3, like that. And now this lack of an element here, this lack of a number here is not equal to 3. So that doesn't make sense. But we're using both the rules here now. Because both of these are now vectors, they're not matrices, they're one-dimensional. So the first argument is promoted to a matrix by prepending a 1. So this is the first argument here, it's array 1. So we're adding a 1 over there. And now this second argument is promoted to a matrix by appending a 1, by adding a 1 to the very right. So now it'll make sense. You have 3 is equal to 3, and then the resultant matrix will be 1 by 1. So if we print out the result, we get 32. It makes sense, it's 1 by 1. All right, now let me explain why these values have different dimensions. So in this one, if we print the shape of the result, we get 1, 1. If we print the shape of the result here, we get 1, and if we print the shape of the result here, we get nothing. So the shapes are different. Even though the values are the same, the shapes are different. Now why is that? All right, let's start with this one, this first one. Numpy hasn't had to do anything to change that. It hasn't had to use these rules to do anything with it. Because these are both matrices, these are both two-dimensional. So when it prints out the result, it keeps the same number of dimensions as the inputs. This has 2 dimensions, and this has 2 dimensions, so it keeps the same number of dimensions. This is the most standard result, essentially, where Numpy doesn't have to do anything with it. With this second one here, Numpy has had to use one of the rules to change one of these arrays. This first array here is one-dimensional, so Numpy has to change it to a 2-dimensional array. And because it's in the first argument, Numpy has had to use this rule here by prepending a 1. So previously the shapes were this, 3, and 3, 1. And then once Numpy has prepended a 1 to the first argument, we get this result. Now, afterwards, it says, after matrix multiplication, the prepended 1 is removed. If we print it out, we get, oh actually no, it's the shape there. If we print out the result, we only get one bracket here instead of two. This is the first result, or this is the first values for the arrays. Once Numpy has added the extra dimensions, the arrays look like this. Because array 2 is exactly the same, but then array 1, this one is 1 by 3. And array 1, in this row here, in this cell, will have changed to look like this one. So once it has done that, it has to remove the dimension, because it added a dimension here. Like from here, it added the dimension to get to this one, but now it has to remove it. So after it has done this calculation, and it has received this result, it removes one dimension. With this second, or this final cell here, both of these vectors are one dimensional. So Numpy has had to add a dimension to both of these vectors. So it has added the dimension to these vectors. It's going to get these vectors, and then it's going to perform the matrix multiplication, and then it's going to get this result with the 2 dimensions, but it removes both those dimensions because it has added 2 dimensions to these cases. So it has to remove both the dimensions, the 2 dimensions. And that's why we're left with an array with no shape. That's why we're left with just the value. Let's take a look at some more examples. All right, now we're going to actually look at some actual matrices. Now we're going to look at the matrices that have values in their rows and their columns. Let's take a look at this one. So array 1 is a matrix. It's 4 by 3. Array 2 is a matrix that is 2 comma. And the reason it's 2 comma and not 1 comma 2 is because it's only one dimensional. If it looked like this, then it would be 1 comma 2. Let's print the shapes. So we get 4 comma 3 and 2 comma. And again, 4 comma 3 is first because we're specifying array 1 in the first argument. So if I write this up here, we get 4 comma 3 and then 2 comma. Now this second argument here, it's one dimensional, so Numpy has to append a dimension because it's in the second argument. So we add a 1 there. This does not make sense because 3 is not equal to 2, so matrix multiplication will not work. If we print it, we get an error with the classic value error here. All right, so we can skip this one because it doesn't work. Okay, we have, I believe, the same matrix as before. Yeah, the same matrix as before for array 1. But then array 2 is also a matrix here because it's got the 2 dimensions, but it's different. And now it has 3 elements in it. So if we take a look at the shapes, array 1 will be 4 by 3. And then array 2 will be 3 by 1. The k's are equal. This one will make sense, and it's going to result in a 4 by 1 matrix. Let's print the result. That is the 4 by 1 matrix. Now, if you're familiar with matrix multiplication in maths, you'll probably understand what's happening here, but I'll just go through it. What I've done here is I've copied these arrays over here. So array 1 is this one, and array 2 is this one, and that's just so you can see them side by side. Now, what it's doing is it's taking dot products with sections of the matrix and this vector here. It's going to take a dot product with this first row and this column here, and then it's going to store the result in the output. Then it's going to take a dot product with this second row and the same column, and it's going to store that result in the output. Then it's going to do the same with these 2 rows here, each separately taking a dot product with this column. That's what I've written here. So the result is 140, 320, 500, 680. And I've written how we get to those results. So 140 is taking 1 times 10 plus 2 times 20 plus 3 times 30. And then 320 is taking 4 times 10 plus 5 times 20 plus 6 times 30, and so on. Now I just want to explain why we're getting this shape for the resultant matrix. The first reason for that is by just using this rule. As long as k is equal to k, then we're going to get this result here, 4 by 1. And 4 by 1 is a column vector or a column matrix. And that's this one here. It's going to move down the columns. But the actual inherent reason for why that is, like that's just using the rule. But why that is because when you take a matrix multiplication, as you move down the column here, so as you take different rows, you move down the column in the resultant matrix. So that's kind of a visual way to look at it. So this first one, 1, 2, 3, taking a dot product with 10, 20, 30, that one is at the very top. But then you move down one element in the column, which is taking the next row. So each of these values here are in the separate elements of the column. As you move down there, you also move down in the result, in the output. Equivalently, and I'll show you this later on in another example, as you move down, or as you move along the row in this second matrix here, so as you move to the right, you're taking different columns essentially. Then you move to the right of the output matrix. Now in this one, we only have the one column. So we're only going to get the one column in the result. But if we had multiple columns here, then we would get multiple columns in the result. That's the way that it works here. And now I'll show you, well, this example here first. Okay. Now what is the difference with this one? Okay, so the array 1 is the same, but array 2 is now a row. Array 2 only has one dimension. And what we're going to do is we're going to take matrix multiplication with array 1 and array 2. So let's take a look at the shapes. Well, array 1 shape is going to be 4 by 3 because we have 4 elements in the column and then 3 elements in the row. And then array 2 is going to be just 3 comma because it's only one dimensional, so it's not going to be 1 comma 3, it's just going to be 3 comma. Array 2 is one dimensional, so Numpy has to use one of its rules, and because it's in the second argument, we're using this rule, and we're adding a 1 to the very right, so we're going to add a 1 here. Alright, 3 is equal to 3, so it works. Well, it will work, and we're going to get a 4 by 1 result. Let's run this. Well, hang on, I said that we're going to get a 4 by 1 result, but we got a 4 comma result. If we print the shape of this output, it's 4 comma, it's not 4 comma 1. So am I lying here? Am I doing anything weird here? Well, this rule, what it specifies is it tells you the result right after this matrix multiplication is performed. So if once array 1 is matrix multiplied by array 2, this is going to be the result. And what's going to happen is after Numpy has performed the rule, which is converting this to a 2D array, then what these are going to look like is they're going to look like these. Because they're the same values, but here array 2 is 3, 1, and here array 2 is also 3, 1, once Numpy has converted it. So it's going to look like this, and then when we matrix multiply it, it's going to give this result. So it will give 4, 1, which we're seeing here. But the reason that this one is not 4, 1 is because this second array, in this case, had to be changed in this way. So it's promoted to a matrix by appending a 1, but then after matrix multiplication, the appended 1 is removed. So essentially this rule works right after the matrix multiplication is performed. So this is the dimensions. As in when I say the rule works, this is the dimension of the resultant matrix, the resultant array, 4, 1. But then Numpy has to do this. Numpy has to remove the appended 1. And then once it removes the appended 1, we're going to get just this this result here. So instead of this value here, which is 4, 1, we're going to remove the 1 and we're going to get 4, comma. If we move back up here, I'll just show you what that looks like. Once it gets this result, it's going to squeeze it, which means it's going to remove the added dimensions. That's what this function does. And if we print numpy.squeeze on this, we get this one, which is exactly the same as this one. Okay, another example. Now what we're doing here is we're matrix multiplying array 1 by array 2. That's what I've written down in this cell. This is array 1, which is equivalent to this one. And then this second array is equivalent to this one. Will this work? Let's look at the shapes. Array 1's shape is 3, 4, and array 2 shape is 4, 3. Now this will work because 4 is equal to 4, and we're going to get a 3 by 3 result. Let's print this. We get a 3 by 3 result. In this first element here, we're multiplying this first row with this first column in each of the respective matrices. So it's 1 by 1 plus 2 times 4 plus 3 times 7 plus 4 times 10. That's this one. So as I said earlier, when you move down the column of the first array, so this is down the column, this is the first element in the column, this is the second element in the column, this is the third element in the column, or 0, 1, 2 if you use the indexing that Python does. You'll move down the column of the resultant one. So 1, 2, 3, 4, taking the dot product with that with 1, 4, 7, 10, that's up here, that's 70. And then 5, 6, 7, 8, taking the dot product with 1, 4, 7, 10, that's 158. That's below 70, that's down the column. And then when you move to the right of the second matrix, which is through the row, so you're taking different columns, you're taking, I mean, there's different ways to look at it, but it's essentially, you're moving through each element in the row. You know, so you have 1, 4, 7, 10. Those are all the first or the 0th element in each row. And then 2, 5, 8, 11, that's the first element. And then 3, 6, 9, 12, that's the second element. So essentially to the right. When you're moving to the right of this second matrix here, you're going to move to the right of the resultant matrix. And that's what I've written here. 80 is 1 times 2 plus 2 times 5 plus 3 times 8 plus 4 times 11. And the same pattern will follow for the rest of these. So if you move down 2 times here and you take the dot product of 2, 5, 8, 11, which is moving to the right once, then the result will be over here, 2, 8, 8, because you moved down twice and you moved 1 to the right. All right, so that's this example. What is the difference here? These are the same arrays. The only difference is that array 2 and array 1 are switched here. And here I've shown what's actually happening. So these are the same arrays over here in this example, but they're just switched around. So the argument 1 is now array 2 and the argument 2 is now array 1. Let's print the result. And we get a result which is a different shape to this one. When you switch the arguments around, it won't necessarily be the same result. And it usually won't, and sometimes it won't even work. And I'll show you again another example of that. Let's look at the shapes. So array 2 is now on the left-hand side, so we do array 2 first. It's 4 by 3. And then array 1 is on the right-hand side, so that's 3 by 4. 3 is equal to 3, and we'll get 4 by 4 as the resultant matrix. And this follows the same pattern in terms of moving down or moving right for this example. So like 1, 2, 3, taking the dot product with 2, 6, 10, that's going to move to the right. And then moving down here to 4, 5, 6, taking the dot product with 1, 5, 9, that's going to be this value here, 83. Another example. And this one demonstrates that it won't always work where you reverse the order of the arguments. Now, array 1 is exactly the same as this example. Array 2, on the other hand, we've added another element in each row. So it used to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But now it's 1, 2, 3, 10, 4, 5, 6, 100, 7, 8, 9, 1000, and 10, 11, 12, 10,000. Firstly, we're going to multiply array 1 by array 2. Matrix multiply, that is. Array 1's shape is 3, 4. And array's 2 shape is 4, 4. 4 is equal to 4. This will result in a 3 by 4 matrix. If we print it out, that is the result. Okay. If we reverse these around, so instead of 3 by 4 being matrix multiplied by 4 by 4, we're going to reverse these around. So it's 4 by 4 and 3 by 4. 4 is not equal to 3. So it will not produce a 4 by 4 result. If we print this out, we get an error giving us the classic, value error, saying that the dimensions are not matched properly. What I'm trying to demonstrate by showing you this example as well is that it won't always work when you switch the arguments around. Now, a way to fix this is if you have this first argument, 4 by 4, we can't really do anything to change the dimensions around, because if we transpose this, it'll still be 4 by 4. But the second one here, we can transpose it to become 4 by 3. Transpose, if you don't know, is just switching the rows and the columns around with relevance to a 2 by 2 matrix anyways. So if you have a 3 by 4 matrix and you transpose it, let's just take a look at array 2. And if we transpose array 2, oh hang on, it's not array 2, it's array 1. There we go. If we transpose array 1, then 1, 2, 3, 4 is now going to be along the column, 4, 5, 6, 7 is going to be along the column, and so on. So essentially we could do this to array 2 as well, but what I meant by saying it won't be useful is that it'll still be the same dimension. The values are switched around, so 1, 2, 3, 10 is now down this column, and 4, 5, 6, 100 is now down this column, but the shapes of both of them are the same. So if we switch this around, it still will give us an error if we try to matrix multiply it. But now, so this here was the shape of the original one up here. If we transpose it, which is what we've done here, there's a lot of stuff on the screen, but we'll remove that. So we transpose it and then take the shape. Now we have 4 by 3. And if we write this up here, now it'll work because 4 is equal to 4, so we'll get a 4 by 3 matrix. So instead of taking array 2 in the first argument and array 1 in the second argument, we keep array 2 in the first argument, but we take the transpose of the second argument, and now it'll work. Note that this won't always work. It really depends on what the dimensions are. So those are the examples for matrix multiplication in 1 dimension and 2 dimension. Next time we'll look at the behavior for 3 dimensions and dimensions after that as well. I might do those in separate videos as well, because I imagine once you get to higher dimensions like 5 dimensions, it'll get a little bit more complicated. Anyways, thank you for watching.